Example problem 3.4. It says the lateral surface area S of a cone is given by S equals pi times R square root R squared plus H squared. Where R is the radius of the base and H is the height, determine the radius of a cone that has a surface area of 1800 meters squared. So I guess it'd be S. And a height of 25 meters. Solve by using the fixed point iteration method with R equals S divided by pi R squared plus H squared. Okay, so that actually makes it really easy. They gave us the update equation. There are a couple of alternatives that you could use for fixed point iteration. Some of them converge, some of them diverge. There's no promise any of them converge. Start with R equals 17. Man, they're giving you everything right off the bat. I'm going to calculate the first 4 iterations. Well, we're going to do this in Matlab and do probably about the first 40 iterations because why not? This is where we left off the last example. I'm going to steal this little iteration loop, put it in a new script. Let's start with our instructions and just do the first 4. But let's update the update equation to match this problem instead of being the other. So R, call it R of I plus 1. Okay, we can use R's. That's okay. All right. Equals S. So in this case, S was told we were told it was 1800. Everything else in the denominator. Pi. I think pi is just a built-in variable. Am I mistaking my programs? Nope. Pi is saved in MATLAB as just pi, so we can use that. Pi. So denominator pi times. This is going to be square root. In fact, we'll do the functional value of it. Square root of R of I squared plus H. Well, actually, H was given to us, right? So H was 25. It's a constant, but might as well just put it there. Let it square it each time. You could save a few cycles if you wanted to go ahead and pre-calculate that, but I don't care. It'll work. Hope it works. Okay, so this will go from A equals 1 to 4, so just basically 4 loops, update equation specified to us, I equals I plus 1. We should be able to read out the R's. Hope it works. I have to save this. Let's do this as fixed point example. Oh yeah, I do that every time. I always forget that it can't handle spaces, but okay. Good. It's broken. You need to initialize. R of I. Is there? Oh yeah, it told us the first one. R of 1. Well, that's my mistake. Happens. I'm leaving it in the video. Imperfections exist. Attempted to access R of 51. Did it X out of bounds? All right, I figured it out. Do you know why it tried to access R of 51? We should look at what the present state of the variable I is over in our workspace. Whoops! From the previous function, left I having a value of 51, did not reset it right here before I'm working, so I equals, I guess what it needs to be 1 initially. All of a sudden this thing works a lot better. In fact, following the example, these numbers line up exactly as you'd expect them to. The first guess was 17. Second guess solves down to 18.95. Third guess, 18.263. Yep, still right on track with the correct answer. 18.506. And then 18.420. So this does not show that rapidly expanding divergent behavior we have to worry about. These are converging onto a single point. So that's good. Let's go ahead and expand out the number of iterations and see what happens when we go to 40. Well, 18.4428, blah, 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 numbers. They're all pretty much the same. So you have to go back, what is this like? To step 4, you're just fine-tuning the answer all the way down. In fact, to the number of digits displayed, there's no change after, so it'd be 31, 32. After the 33rd iteration, we've converged it to, that's 4, 8, 12 digits. Plenty enough, but hey, that's overkill. Let's look again at the time required. So tick. Talk, pretty nice little tool. I still like that. It's so easy. 9/10,000ths of a second. So that worked well. That's all there is to it. That is using fixed point iteration method on problem 3.4. Of course, this was spoon-fed to us. The hiccups and the gotchas for the fixed point are that the orientation of the fixed point iteration function you selected, of which this function had two options, would be unstable. We never had to check on this function if the derivative was less than 1 of the iteration function, and they gave us, spoon-fed us the initialization condition. In fact, let's see if it breaks if we do something else. I'm going to take this back down to about 20. Nope, that still worked. Let's take this down even farther, 10. Let's initialize it, something way out there, like 50. No, that's still totally stable. It's supposed to be a very, very stable problem. 200? Nope, still found it. Okay, how about negative? Negative 200. I tried to break it, guys. I really did. Still the same value reading out. Okay, code works. Very nice. Job done.